Hi students, today I am going to explain in electrophilic aromatic substitution reaction. In the last video I already explained what is halogenation, nitration and sulfonation, and today I am going to explain Friedel-Crafts alkylation reaction and Friedel-Crafts acylation reaction. So what is Friedel-Crafts alkylation reaction? So RX, which is an alkyl halide. So when benzene reacts with the alkyl halide, maybe this halides may be chlorine, bromine, etc. in the presence of aluminum chloride or iron, iron chloride or any halide FeX3. So it will give benzyl alkyl plus HCl. So we will see one typical example to explain this. So when benzene reacts with tertiary butyl chloride in the presence of AlCl3, which is a catalyst, it forms third butyl benzene and hydrogen chloride is formed. So it is the product. Third butyl benzene is the product. Let's see its mechanism. So as usual, as I explained in the last video also, the mechanism is same with little differences. So first step is electrophilic formation. So how the electrophile is generated here? Very simple. Our tertiary butyl chloride. So tertiary butyl chloride reacts with AlCl3. So these two react with each other to form a complex. So complexation takes place to form a complex intermediate. So in this again the living group dissociation takes place and electrophile is generated. So this electrophile which is generated is a carbocation. So this carbocation will attack the benzene ring. So the next step, that is step 2, is electrophilic attack. Here the benzene will be attacked with the electrophile which is generated here. So to form a resonance stabilized intermediate, which is we call sigma complex also. So this resonance stabilized intermediate in the third step. So we, as I already discussed, while the formation of this resonance stabilized intermediate, when the electrophile attack, it loses its aromacity. So to restore its aromacity in the step 3, it will lose one proton. So proton transfer will take place. So in the presence of AlCl3, so the proton transfer will take place to form the tertiary third butyl benzene. So to form third butyl benzene is as the product. So this is the mechanism. As usual, we saw in the halogenation, nitration, sulfonation, the same is repeated. Then what is the difference? The difference is here the electrophile which is formed is a carbocation. So the electrophile which is formed is a carbocation. Then what is the problem with the carbocation? So when we get a carbocation, it will be easily rearranged to form a stable carbocation. So what happens? It is a problem. So, and one more problem is when the product is formed, it will become more reactive. So for example here, benzene reacts with CH3Br. So in the presence of FeBr3, for example, we'll get methyl benzene, which is more reactive than benzene. Again it continues its reaction for more methylation. So in the two positions, again in the two ortho positions and meta position, again the methylation takes place. It continues so that we'll get a mixture of all the possible products. We'll not get a specific product, we'll get a mixture of all possible product, and separation of this is very difficult. So this Friedel-Crafts reaction, alkylation reaction, is difficult to conduct in a lab. So it is failed. So next is Friedel-Crafts acylation reaction. The only difference between Friedel-Crafts alkylation and acylation is here instead of alkyl chloride or alkyl halide, we use acid halide or acyl halide. So what is acyl halide? RCOCl. Here I took chlorine. So reacts with benzene in the presence of AlCl3, which is a catalyst to form the product. So as usual, here also the formation of electrophile is the first step. So acyl halide or acid halides reacts with the catalyst AlCl3 to form a complexation. So complex intermediate will be formed. After the dissociation, leaving group will dissociate to form electrophile. So this electrophile will attack the aromatic ring. The difference between the alkylation and this acylation, Friedel-Crafts alkylation and acylation, is there the carbocation formed will be rearranged, and here the electrophile formed is not a carbocation. So that is the difference. And so let's see the step 2. So the benzene reacts with the electrophile formed. So electrophilic attack takes place and the resonance stabilized complexes like a sigma complex is formed, and it will lose its aromacity. So to restore its aromacity in the third step, proton transfer will take place. So to form the final product. So here the final product which is formed is not more reactive like in Friedel-Crafts alkylation reaction, so that multiple products will not be possible. It is a stable product is formed here. So it is easy to carry out. Why? Because of the presence of C double bond O. So which is a deactivating group. In the last videos I already discussed what are activating groups and deactivating groups. Activating groups are which make the benzene ring more reactive than the normal benzene. Deactivating group means which will deactivate. So here it is a deactivating group. That's why it is not more reactive and it is a stable form. And here in the Friedel-Crafts reaction it is a activating group, that's why it will become more reactive and so many possible products, so many mixture of products will be formed. So that is the difference between Friedel-Crafts alkylation and acylation. So we will just see the differences between alkylation and Friedel-Crafts alkylation and acylation reaction. Here the substrate is alkyl halide RX. Here the substrate is acyl halide or COX. Here the typical catalyst same for both AlCl3 aluminum chloride or iron chloride FeCl3. So what are the complications here in the alkylation reaction is here C plus carbocation which is formed, it will rearrange. So that is one problem, and we can see multiple alkylations because the final product which is formed is more reactive and it will continue to form alkylations continuously. So many products will be formed. We cannot remove the final product correctly. And here in acylation nothing is happening there because of the presence of CO group which is a deactivating group. So that's why we'll get a good product. We can easily isolate the product. So we can sum up that so alkylation is having so many problems, whereas acylation is a good one. So we can sum up that alkylation and acylation reactions are similar with a minute differences in between them in their mechanism. Thank you.